Hi guys, so this is the preceding part of our video. So in this case, we have a problem that is a plane truss. Again, solving with the grass software. On this problem, all members are double angles with 4 by 3 by 3 over 8 short legs back to back with an area of 4.97 inches squared with a moment of inertia that is 3.84 h to the fourth and a y top is 0.782 inches with a modulus of elasticity that is 29,000 psi, the unit weight that is 491 pound per cubic foot, and a coefficient of thermal expansion that is 6.5 times 10 raised to negative 6. So here we can see this is our the figure or the structure that is with respective loadings at specified points or nodes. We'll use this again as a basis in plotting it to the grasp software. In this case, we are tasked to determine the reactions at T, the vertical and horizontal reactions, determine the actual force in bar AE, so basically this horizontal one AE, and bar BE, this one. And then determine the nodal displacement at C, the horizontal and the vertical nodal displacement. Let's proceed to our software. So here's our software. So what we're going to do first is we're going to define and the structure as a truss. So actually I will define this as truss. Then I'm gonna put a I'm gonna show grid as lines for me again, my own reference to set as a basis in plotting the nodes and the lines. However, we need to also check whether the units is in a customary unit, since our problem is in a customary units, using customary units problem. So that's okay. This x. And so we're going to define first our first point. That's no problem. That's point D. So this is our reference point. That's our origin. Then we are going to, from the problem, we're going to see that the spacing or the proportion or actually the length of these members are 4 at 15 feet. So there are 4 spreaded members at 15 feet length. So we're going to do that. So I'm gonna first count 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Then I'm gonna put some, I don't know. Before that, I'm gonna set a material. Add a material with the given properties of the plane, the material that is used in this plane truss. So I'm gonna use a steel. Let's say it's a steel. With its modulus of elasticity of 29,000 psi, with a unit weight that is 491 pounds per cubic foot. 91 pounds, and the coefficient of thermal expansion is 6.5 times 10 raised to negative 6, is approximately 0.000065. And so we click OK and then close it, and then yes. So here we're going to add a member, and then I'm gonna define these members with its properties, cross-sectional properties. So I'm gonna use the AIY given with the I actually ground my reference to the given properties, the material properties in the problem, since it requires the input for the inertia, the YT, the area, and the depth. So I'm gonna use the AIY. So here the depth is 4, since it's 4 by 3 by 3 over 8. So this is 4. Our area is given, actually, that is 3.84 inches. 4.97 inches squared. This is 4.97. Our moment of inertia, that is 3.84 inches squared, 3.84 inches to the fourth, and our y top dot is 0.782 inches. 0.782 inches. Then we click OK, and then we're going to use the sectional material as a default for new members to be added, because I'm going to add the members simultaneously. So I'm gonna click OK. So here in the figure we can see, in the figure we can see that this is how I'm going to orient myself in constructing the figure using in the software. So I'm gonna solve first. I'm gonna construct first this vertical one that is 20 feet. So here I'm gonna count 20 feet. That is 20. I'm gonna add a node. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 20. So that's a node. Then I'm gonna add a member. This is supposed to be 20 feet. So I'm gonna check if the dimensions are correct. Now that's 20 feet and that's correct. Along with this, that's 15 feet. So that's correct. I'm gonna remove the dimensions. And then I'm gonna put a member here. Then I'm gonna make a 30. No. I'm gonna execute a member array in this member that is on the horizontal with a 15 feet. Now I'm gonna use first a 15 feet. 15 feet to generate that 3. There's already one existing, so we need 4. So I'm gonna add 3 and then generate. So as you can see here, it generated a member 3 additional members with its nodes. So I'm just gonna continue plotting this points until we get the whole structure, all parts of the structure. So I'm gonna add nodes again. Add nodes. So here I'm just gonna have to plot this in a compatible way, and then put the members. And then this. And then this. And this node, I'm gonna remove this. I'm gonna remove this node since it will probably cause an error to my delete member on. And it will cause an error upon executing structural analysis, since stiffness matrix on this truss structure will be undefined, or will not be defined by the function or the formula given or the program in this software. So let me add the let me check if the materials are correct. Double check so they're correct. So I'm gonna proceed with adding the supports. So this portion, the supports here are pin supported. I'm gonna just add okay. And the other side at point G, so I'm just gonna add a roller support. So row support, and I click OK. And so this is our structure, and then we're going to add the loads, or the point loads. Actually, the loads here are only point loads. I'm gonna add point loads here. So this nodal point, this is a point C. There's a load at a horizontal direction that is, in the horizontal direction there's 2 keeps. So given the orientation here, going to the right side is positive, so I'm going to have a negative input since the orientation of the load here applied in the problem is going to the left side, that is negative. So I'm gonna put a negative 2.0 keeps. 2.0 keeps. Then I click OK, and here we can see already the applied loads. I'm gonna set the grades as dots for a better orientation and viewing view on the space, or let me say the window. And then I'm gonna add another load here that is along the y-axis going downward, that is 1.2 keeps, 2 keeps. Then okay, and here at point F, at nodal point F, that is 1.5, that is still going downward, and click OK. So we have successfully constructed our structure. Now we are going to perform an analysis, but first we are going to to analyze this whole structure as a truss, since this is a plain truss. Then we're going to perform before performing analysis, let us remove the unused nodes if ever, and then run an analysis. And it will require us, of course, to save the data before running an analysis. I'm gonna put here a problem B, it's PB. So let me save this, and then it will show us the results. So what are we required to get here is basically the reactions at D. So this is the point D. So in our structure, result values, I'm gonna change the views, then the node numbers. So here we are tasked to find the reactions at D. Reactions at D, both the vertical and the horizontal reactions. Vertical and horizontal reactions. Here we just have to top the reactions, command reactions, solving for the reactions at point D. So our point D here is our node 1. So as we can see in the figure, in the orientation of the figure, the label on the figure, that's node 1. So at point D, our reaction, the vertical and horizontal reactions are 2 keeps, and for the horizontal reaction, that's 2 keeps, and the vertical reaction is 1.94 keeps at point D. So we just have to put give an input here. The horizontal, that's 2 keeps, 0.00. Let's put a red color in it. And then our vertical reactions here are 1.94 keeps. 94 keeps. Next is we're going to determine the actual force in bar AE. So this is our bar AE, this vertical one, next to the nodal point D, that is E, and a vertical connection member, a connection, as well a vertical connection that is in a member, that is AE. So we're going to determine its actual force along with the BE, this a diagonal one. So the member AE, so here there's a member AE, we're going to determine its the actual force, the actual, that's the actual force. So upon attaining the exact result, this is for AE, I'm gonna just have to top this member to generate an exact result, the AE. So here at the full length, that is 20 feet. 20 feet is a member. So the full length, there is an actual force that is 1.942. So I'm gonna put it here, 1.942, because that's how the values are presented as presented, or the output of the analysis. Sorry for this. I'm just gonna put an input for another input for BE, member BE, so this diagonal one. So I'm just gonna close it, and then we're going to tap this member to view the actual force of this member BE. So this is member BE. This is our member BE. So the actual force here, that is negative 0.927. So basically, now the orientation on assigning whether the force is negative and positive is when the diagram shows where the diagram of the force is under the structure, it is negative, regardless of negative, but when it is above the structure or the member, it is a positive. It's a positive force. So in this case, it is an actual force. So since it is in this below this member, so it will be a negative actual force, that is negative 0.927. So I'm gonna input here is the answer. It's negative 0.927. Sorry, 0.927. And then finally, we're going to determine the nodal displacements at C. So mind that at point C, there is a nodal loads. That is horizontal nodal loads going to the left. That is a negative. So let's see the displacement. Those are actually horizontal and the vertical displacements. So we're going to find that to look for to command the software to show the deformed shape in order for us to determine the vertical and the horizontal reactions at point C. So I'm gonna zoom it here to have a clearer view. What's happening? So here our at this node our horizontal and the displacement, the horizontal and vertical displacements are negative 6.4 times 10 raised to negative 0.3 inch, and y, that is negative 7.8 times 10 raised to negative 0.303 inches. So I'm just gonna put it here for the vertical one, horizontal, that's dx, and displacement x, displacement along x, that's negative 6.4. Negative 6.4 times 10. I'm just gonna put e, as exponent e, and then times exponent e, that's negative 0.3, negative 0.3. And this is not really a good orientation, no? I'm just gonna, the most proper one is negative 0.3. Then I'm just gonna copy this. That's 7.8. 7.8. There's a negative 3. So that's it. We were able to determine our objective upon executing this or having an structural analysis using this plane truss using the GRASP software. So I hope you have learned something in this video. Thank you for watching. Bye.